So what I'd like to tell you about is actually, for I think the last 50 years, we've had an excellent understanding of bosons and fermions, and now, with the advent of quantum Hall systems, of course, anyons themselves, as we all know quite well, have become very important and interesting. So what I would like to do in this talk is to really borrow from the knowledge that we have, from bosons and fermions, look at what kind of correlations they obey, and sort of ask similar questions for the case of anyons, and also do it in a sort of realistic physical setting, which would be amenable to actual experiments. So these are the sort of correlators I'd be interested in. And the beam splitter would be one example of a realistic physical system that's been studied very well for fermions and bosons. And what I'd like to do is to say, how could you come up with this kind of setting for anyons? And it turns out to be non-trivial, and what results we have seen. So, and these are my collaborators here on two different projects. So I don't need to give an introduction here, and in the morning we already had the definition of abelian fractional statistics. That's what I'll restrict this particular talk to. It's just that under exchange, you gather this additional phase where alpha equals 0 would be bosons, alpha equals 1 would be fermions. And so now the question, we're looking at any fractional value of alpha. So I think, there's been a lot of exciting development also on the experimental side with regards to really probing these fractional particles. And I think the first evidence that really came in any experiment, I would say, for these fractional particles really started off in the 90s, where two edge states were brought close together. And if you look at the short noise due to quasi-particle scattering, you can see that these particles actually have fractional charge. We know that there's been a lot of complications since with these kinds of experiments, but at least I think this was one of the first motivations to really try to start looking for these particles in the quantum Hall system. So this is for fractional charge, but the thing that we're really interested in is we're interested in both, but it's really, at this point, fractional statistics that really needs to be sort of unequivocally demonstrated in the quantum Hall system. And there have been a lot of different proposals. This is actually the abelian version of the sort of things that we've been discussing here. So it's not really looking at the same kind of interference that you'd look at in the non-abelian case. What you do in this experiment, at least the proposal, is that by changing two different parameters, you can see that quasi-particles doing the tunneling here have both fractional charge and fractional statistics. So that was sort of the idea behind this proposal here. This proposal here actually looks at three edges, and so this is a quantum Hall fluid, these are the edges, and you could, for example, look at the partitioning of current from one source into two edges, and when you actually look at the current-current correlation between these two, you can see statistics coming in here. So that was this proposal. And then this one I won't go into too much detail. It looks like a completely wacky geometry. What's wonderful is that the group there's a group in Israel in the Weitzman that has actually realized this sort of setting, and the proposals here are based on this kind of setting. So these, and as far as I know, there hasn't actually been any experiment done that's completely confirmed that these quasi-particles actually do have fractional statistics. There have been some results, and as far as I understand, there's still an issue on how to interpret these results. Okay, so this is sort of the picture as to what's going on the experimental front, what the proposals are. And what I'd like to do is really to step back and say, what is the common underlying feature in all of these? What is the most basic thing you need to look at to really figure out whether particles have fractional statistics or not? And only a BPM this for this particular talk. So if you look at each of the concepts here, every one of them actually has, obviously, you need two particles. So if you go back to the underlying concepts, again, in the fermion and bosonic case, this has been explored in a lot of detail. And for example, historically, I would say one of the first explorations for bosons really came with Hanbury, Brown, and Twiss, where what they did was to, they weren't actually looking for quantum statistics, but it was something that was buried in their experiments. So you look at photons coming from two incoherent sources and essentially ask what is the intensity correlations between photons that are collected here and photons that are collected here. And it was a really impressive set of experiments that were done with these actual sort of radio interferometers. And the idea is that as you change the separation between the interferometers, the correlations die down, but the correlations actually really take into account the fact that these photons are bosonic. And just, by the way this was done is they had this long railroad, and these radio interferometers were actually separated or brought together on these rails. Hanbury, Brown, and Twiss also did a tabletop version of the same experiment, and it's really sort of the underlying thing that's used in modern day quantum optics, and essentially it's the same thing. You have two sources and two detectors, and what happens is that photons can come in from either source and go into the two detectors, and the sort of questions that you ask are, if one photon goes in here, what is the probability that another one goes into the same detector as opposed to the other detector? So that's one more place where you actually see photonic statistics, and now also fermions have also been explored in the same setting. And then, for example, if you go to nuclear physics and you look at scattering cross-sections, you can see that if you look at the scattering cross-sections, say for two identical fermions, 90 degrees happens to be a very special angle at which these fermions don't scatter. And again, I'll explain that a little bit more, but the underlying principle is that these are fermions that have exclusion statistics, and so 90 degrees ends up being a very special angle at which they cannot scatter. Okay, so all these are things that you find we've looked at this in great depth in the boson and fermion case. What I'd like to do is to sort of step back and say, what are analogous things that anions in the quantum Hall bulk might actually, what are the analogous things that they would reveal if instead of bosons or fermions you took anions in the quantum Hall bulk and looked at similar correlations? Okay, so what I'd like to do towards this end is to first introduce a very simple model. So what I'm doing here is actually very simple. It's just a system of two anions in the lowest Landau level, and ask what is the physics of these two anions. And in fact, this is something that's been studied quite a bit by people here. But based on the behavior of these two anions in the lowest Landau level, you can ask the same sort of questions that were being asked for the case of fermions and bosons. So in particular, I'll ask what are the bulk correlations like? Where do you see signatures of fractional statistics? And ultimately, how are these correlations related to the kinds of experiments that have been proposed with edge state quasi-particles and the like? So that's what I'll do in the first half. And then in the second half, what I'll show you is a setup in which you can build an anionic beam splitter in the lowest Landau level and ask the same questions as to whether you have bunching behavior or anti-bunching behavior. If two particles started off from two sources, would they go into the same detector or would they go into different different detectors if these were anions. So this is sort of essentially the roadmap with regards to where I'm headed. Okay, so again, like I said, what I will be discussing here today is just 2 anions in the Landau level, so it's extremely simple, but as we all know, this is highly relevant to the quantum Hall system with all the electrons and everything, because there's really a one-to-one mapping between quasi-particle excitations in a realistic quantum Hall system with all the electrons included, and the effective anion model that I'm going to talk about, where I focus only on the anionic degrees of freedom. And there's a lot of work. I should say that in the last few months in figuring out all this, there are these 2 references that I've been carrying around and using almost like the Bible, so it was really very nice to meet Hans now, because he was one of the authors, so it was really great to actually have discussions on their constructions in person. Okay, so like I said, the model that I have is very simple. It's just 2 particles in a magnetic field, so maybe particle 1 and particle 2. And here I've written the whole thing in relative and center of mass coordinates. So even in the center of mass and relative coordinates, the 2 particles completely decouple. So this is the center of mass, this is the relative coordinate, and Q is just the charge of the particle. So you can see that there's a slight difference in mass, there's a slight difference in charge, but essentially you have these 2 decoupled sectors. Okay, so now the question is, where do you bring the fractional statistics into this? This is put in as a boundary condition for the wave function. So when the 2 particles, 1 and 2, exchange coordinates, that's the same as taking r to minus r, and so you pick up this fractional phase here. And just to make a correspondence with what happens in the Laughlin case, for example, the charge would just be nu times e, and then the fractional phase would just be mu itself. So alpha would be the same as nu, which would be 1 over an odd integer. It becomes a little more complicated for, let's say, the nu equals 2/5 and the like, but even for that, you could come up with an effective construction like so. Okay, so this is the Hamiltonian at hand, and now you can say, what's the Hilbert space of this sort of Hamiltonian? And for a single particle, you're completely familiar with the Landau level construction, etc., etc. So the center of mass is exactly the same Hilbert space as what you'd have for a single particle. The thing that's subtle is actually the relative coordinate, where you have this anionic boundary condition coming into play. So if you look at the Hilbert space for the center of mass, you can sort of define your guiding center coordinates in terms of these raising and lowering operators. And then if you look at the Hilbert space, it's actually just spanned by usual eigenstates of the angular momentum. And then this is the position representation for each of these, well, it's proportional to it, for each of these angular momentum states. And then finally, if you want to describe a localized anion at some particular point, z, let's say the center of mass coordinate being z, then this is the form of the localized state that you have. And I'm introducing that because it is something that I will be using later on. The localized state is exactly a coherent state, and you can see that it's the same factor that's here that's also. So this is the usual stuff. It's what you're completely familiar with. It's the same as a single particle. Okay. The subtlety now comes when you're actually constructing the sector for the relative coordinate, and what you really have to worry about is this anionic boundary condition. So it turns out that with this kind of anionic boundary condition, this x and y itself is not really well defined. These don't respect the anionic boundary conditions. So the relevant operators that actually respect this anionic boundary condition, this is a little busy, but I will go over it. There's nothing too complicated here. So the relevant operators that actually respect the boundary conditions are just quadratic operators in X and Y. So these are all the operators that would respect the anion boundary condition. And based on these operators, you can actually construct a Hilbert space for the relative sector. So it turns out that they're also eigenstates of the angular momentum operator. The only thing is the angular momentum is not quantized in integer values, but it's actually 2k plus alpha because of the anionic factor. And if you look at these states, it turns out that these operators respect this SP1R algebra. These are just irreducible representations of that particular algebra here. So this was actually work done by Hans and co-workers in this particular, these two papers here. Okay, now if you want to look at localized, yeah, by the way, let me stop. Is it any questions?
So applied to quantum Hall, this is assumed to be a long wavelength theory. It's
Yeah, it is. So a good question is what length scale is this actually valid? So what I'll do is, I'll just assume that even at very short, I'll also look in the behavior at very short length scales, but then a good question would be, when you actually look at the realistic quantum Hall case, where exactly does it break down or not? So that's actually a pretty important issue. Okay, so now if you look at localized states, it turns out that there's really a big discussion on what the appropriate localized states are. Naively, you would usually write down a coherent state and you'd say this is, the appropriate localized state to describe, any of these anions at a particular point. It turns out that that's not the case. The natural localized state that I would write down is, again, you can see the same correspondence that I mentioned, would be this one. It turns out that it's not a coherent state, meaning it's not an eigenstate of generalized raising, generalized lowering operator. And to really understand that, you have to go back to these references where they compare this kind of localized state with a coherent state. Look at the Berry's phase that gets picked up under exchange, and they actually show you that the one that's closer to the quantum Hall system is this particular state here. And then this seems a sort of, if you're not familiar with it, it might seem sort of a little, where is it actually coming from? If you look at the fermion and boson case, that's something that we're all familiar with. We know that for fermions, the wave function needs to be anti-symmetrized. For bosons, it needs to be symmetrized. And you can convince yourself that this is exactly what I've done here. One is for fermions, it's anti-symmetrized. Zero is for bosons, it's symmetrized. And you can show yourself that in the limit of alpha equals 1 or 0, you just get these states. So the fermion would have only odd angular momentum states, and the boson would have only even angular momentum states. So this is sort of the construction that you have for anions in the lowest lambda level. Okay, so this is the entire Hilbert space. Okay, once I have this Hilbert space, now I can start asking the same questions that I mentioned right at the beginning of the talk. What do correlations look like? Where do I see signatures of fractional statistics taken from this particular Hilbert space? Okay. So so any questions on the construction of this Hilbert space? I'm sort of going to use this as the starting point for any of the quantities that I actually do. Okay. So what are the sort of questions that I can ask? If you go back and look at all the proposed experiments that I showed you, you look at the Hanbury-Brown twist operator, etc., all these are actually asking the following question. They're saying, if I have two particles at 2 points, 1 and 2, what is the amplitude for them to start off at 2 points and then propagate to 2 different points? So all these experiments are really, at the heart of them, That's sort of the question that's really being asked. So once you have this Hilbert space, it's actually something pretty straightforward to calculate. So for example, you can say what's the amplitude to propagate, for one particle to propagate from point A to point B. I'll just call that K1. And in terms of the wave functions that I define, it's very easy to calculate. And then more importantly, the two-particle propagator, namely if I have two particles in two initial positions, what is the amplitude for them to propagate to two other points? Okay, so again, I just write down the propagator. It's very straightforward, and I'm doing this in the relative and center of mass momentum sectors. They become completely uncoupled. Okay, so again, using the wave functions that I showed you in the previous slide, I can calculate this for the lowest lambda level. And never mind the form, it's sort of messy. I won't go over it in great detail. I just want to make a comment on this. So this is what you have for the single particle. This is what you have for the two particles. So one comment that I have to make, and if any of you have any insight into this, please let me know. We did it completely in terms of these effective anions. Now, this work here by Laughlin actually derives exactly the same thing. The way he does this is to take the whole wave function, putting in two quasi-particles, and then integrating out all the electronic degrees of freedom. It turns out that it's exactly the same result that he gets. So in some sense, this was a check for us, and it was very nice that taking the Laughlin wave function and looking at this two-particle correlator in using the Laughlin wave function was exactly the same as what we got by just looking at the effective anionic degrees of freedom. So that's just one comment. So it was a nice check for us that it was actually working out to be the same. Okay, so we have this mess of a propagator, and now we can ask ourselves, how do we make sense of this? Where is the physics? How do we actually extract any fractional statistics, fractional charge, or anything at all from these two problems?
Is Laughlin's calculation also a long distance calculation, or is that?
I don't know. The basic ingredient is that he writes out his wave function, putting in two extra flux quanta, and then he just defines the whole sort of overlap of the wave function. Okay, so he just takes this whole thing with 1, 2, and then let's say all the other electronic degrees of freedom. He just takes this wave function and then sort of looks at exactly the same kind of thing. So you would multiply this with these two being in some two other positions. And then integrate out all these other degrees of freedom, and then he gets exactly the same result. So what would you say that is?
I don't know. It's an exact integration or is it an approximation?
Okay, this is where I have the big question mark. If anyone knows, please let me know. Okay, because yeah, that's the answer is I don't know, and if anyone's familiar with that work, I'd love to hear about it. Okay. Okay, so where's the physics in all this? One thing we can ask ourselves is, for example, how do you make sense out of all this? For example, imagine I put the two particles on a ring. Let's imagine that I put them on a circle of radius r, and I started them off at these two particular points, and then they ended up at these two other points here. Okay? Normally, for fermions and bosons, we have very good intuition on how to think of these this particular propagator. So there's two possible processes. One where this went here, and that went there. So that's this process right here. And the other process is the opposite. One where this one went here, and then this one. So that's the other one. You can see that for fermions and bosons, there's a minus and a plus sign. That's where the statistics is coming into play. There's a relative sign due to the statistics here. You can also see that 90 degrees is special because these two paths become equivalent. So that's 90 degrees is the special point where you can have exact destructive interference because these two path lengths end up being the same. So these two have to be the same, and there also has to be a relative factor, which is exactly pi for these two to cancel. So based on that, you can actually see that the special angle at which you have total destructive interference is 90 degrees. And also the special radii at which that happens corresponds exactly to the radii at which, if you look at the Arnav-Bohm flux passing through this, that plus the statistical angle have to equal pi. Okay? So you can actually see that for the fermions and bosons, if you look at where this sort of destructive interference happens, you know, you have some information about the Arnav-Bohm flux and also about the statistics. Yeah.
So should I be thinking of a time evolution that starts and then ends later? Because you had a thought in one of your expressions, which is now gone.
Yeah, thanks. No, that was, okay. The answer is, yes, one needs to be thinking about the time evolution. The problem is that I've confined myself to the lowest Landau level, so all the states are degenerate, which means that the reason that the tau is no longer there is that all these are degenerate energy states. So even though I'm writing out something like this, there isn't any sort of propagation going on because everything is just in the same degenerate Hilbert space. So to see something like this, exactly as you said, you need to get the particles moving, and in reality to do that you have to apply some kind of shallow potential that lifts the Landau level degeneracy. So that's the answer. And later on, when I discuss the saddle potential, you see that that's an example that actually gets these particles moving. Okay, this is for, the analysis is for fermions and bosons. I cannot give you a sort of picture like this for anions just because they're not something as simple as symmetrized or anti-symmetrized functions, but it turns out that they follow exactly the same structure. Namely, if you look, this is a function of r and theta in that circle that I had. So it turns out that 90 degrees is a special angle where you have this correlator going to 0. And then if you look at the radii at which you have these 0 points, that's exactly where the Arnav-Bohm flux plus the statistical angle together, when you look at the phases of these two put together, it's exactly when that equals pi. So this is a bulk correlator, but if you, for example, look at this proposal here, and you look at the kind of interference that's proposed here, it's based on exactly the same principle. It's based on the fact that particles pick up some Arnav-Bohm phase, and then if there's two particles, they also pick up some phase because of exchange, and the two together give them some destructive interference. So the point is, the sort of bulk correlations that you see here are very similar to the kind of things that you see embedded in this experiment. And then another thing that you can see is also that there's exclusion statistics going on. So I can have a slightly different setup where I start these two particles at 2 points here as opposed to in opposite diametrically opposite, and have them end up here. You can see that, for example, let's say you looked at a two-particle sort of correlation. What's the probability that there's one particle here and another one here? So as a function of radius, if you just shrank this, this phi to 0, you can see that this goes as a power law, and this, if you look at the exponent that's coming in, that actually depends on the statistical factor. It turns out that if you take an edge state description and you calculate, for example, density-density correlations and things, those are also power laws, and in fact it's the same exponent that's coming in there. It it's just alpha is the same as mu for an edge state, let's say some Laughlin state. Okay. 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 So this is sort of looking at exclusion behavior. Let me make that a little bit more rigorous and actually a little bit more physical. How do we try to understand this exclusion behavior in a slightly more measurable manner? So one of the things that you can look at is, for example, and this is something that people have seen even in something as simple as atoms, for example. If you have an atom and you said, where would you find 2 electrons in one of the shells, let's say? The answer to that really depends on, of course, the spin. But if the spin was completely polarized, it turns out that you really see Pauli's exclusion coming into play in this kind of thing. So if you made a coincidence measurement of 2 electrons, let's say in an atom, and asked where they were, you would actually see exclusion statistics coming in here. So bosons, so what are the sort of questions we're trying to ask? The question that you could try to ask is, if I have a particle sitting at R1, and I had a particle sitting at R2, and I measured the average distance squared between these particles, it turns out that for bosons, this average distance is actually closer than for distinguishable particles. On the other hand, for fermions, it turns out that these are actually slightly separated. This is really a sort of coming purely from exclusion. So the sort of question you can ask is, you can say, what is the average separation for anions here compared to the average separation if these were actually distinguishable particles? Okay, so this is a sort of question you can ask. If this quantity is less than this quantity, then that means that these actually like to bunch together and they're more boson-like. If this is a negative quantity, it means that you have some bunching going on. On the other hand, if this is bigger than this, that means that there's some kind of exclusion going on, and these are more fermion-like. So essentially, if this quantity is negative, then they're showing bunching behavior. If this quantity is positive, they're actually showing this sort of anti-bunching behavior. So what we can do is we can ask what this quantity looks like for the anions that I presented here, and let me just show you what result we get. It's something that we can calculate exactly, not only for fermions and bosons, but for anions in general, but it's too messy, so I haven't presented that there. So let's just look at this quantity here. As I said, if this is positive, there's an anti-bunching going on. If this is negative, there's a bunching going on. Okay? So I'm plotting this as a function of separation. When these particles are really far apart, you cannot really tell, oh, here's an anion and then there's another one there. One particle doesn't feel the presence of the other, so these really behave the same as distinguishable particles. So you can see that all particles go towards the limit of being distinguishable. So you can't tell that these are indistinguishable or distinguishable as you put them very far apart. On the other hand, for fermions, you can see that fermions, this quantity is always positive, which means that fermions are always sort of repelling each other. There's always an anti-bunching going on. Bosons are always negative, so there's always a sort of bunching that's going on. Interestingly, anions actually do both. Okay, so if they're very close together, you can see that they behave fermion-like, so they're sort of repelling each other. And then beyond a certain point, they go below zero. All anions ended up doing the same thing. They go below zero, which means that they're more boson-like, and then they actually just veer off to the sort of uncorrelated value. So all anions, it turns out, at very short distances show a kind of anti-bunching behavior, but as you go further out, they actually show this sort of bunching behavior, which really came as a surprise to us.
Really? So the bunching behavior is where they go below zero?
Yeah.
It's
Yeah. So
barely visible in the green curve?
yeah. So the point
Unless
is
you take a point like 4/5,
right. So
there's still that feature?
yeah. Wait, say that again.
So if you were to go to 4/5, which is closer to 1,
Yeah.
so alpha being 4/5.
Oh, alpha being 4/5. You're saying? Yeah.
It still
So-
doesn't that feature?
right. So the point is that as you go closer and closer to 1, it behaves more and more like a fermion-like. So it actually shows bunching for a very, very small range, but it does ultimately dip below 0. Yeah. And then also the other thing to say is that this particular value here ended up being exactly the same as alpha, in fact. So you can see here this is alpha equals 1, and it starts at 1. Alpha equals 0, that starts at 0, and indeed this is 1/3 and this is 3/5, which was quite, actually that came as a surprise to us, but you can see in the exact form that in fact at 0 this is exactly alpha.
So, what is the critical value for alpha when it starts to behave, go below 0?
For any particular alpha, you mean?
Yeah. So
Yeah, no, actually, I don't know what the exact form is as a function of alpha. The only thing to say is that...
So my question is, for fermions it's above and for bosons it's below.
Yeah,
And then I see that at some point it's above and then it's below.
exactly. So there is an R critical
So there's a critical point and
Yeah.
you don't know the critical point.
I don't know the exact value, but what I can tell you is that as this value gets more and more close to 1, it keeps getting shifted further and further out.
Hmm.
Yeah. So
So
the reason that I found this a little surprising is that I thought if alpha were less than half, it would look more like a boson. If alpha were greater than half, it would look more like a fermion. This is saying no, that's not true at all. It really depends on the length scale at which you're looking at, and these particles can behave both boson-like and fermion-like, depending. Yeah.
This length scale is always set by the magnetic length?
It's set by the magnetic length and it's set by this fractional statistical parameter. Yeah. And that's what's interesting, that it is the magnetic length and it's also this factor. Those are the only two things that it actually depends on.
Well, I mean, they all kind of approach distinguishable particles, but it has to do something with the width of the wave function of each particle compared to the separation.
Yeah. So actually this is scaled by the magnetic length. You're right. Yes, and then on top of that, it also depends on their statistics. Yeah. Okay, so these were some of the results that we got. And now the question is, I already showed you some experiment. I mean, I sort of related it to some proposals, some of these features. But now the question is, can these properties that I presented, can they be seen in realistic experiments? Okay, so this was the sort of question that you were trying to ask. I already,
Sorry,
yeah.
can you back up?
Yeah.
I'm trying to read some of your previous overheads on
Okay.
slides. But can you back up? I mean, I'm trying to get the definition of Z that you use in this parameter.
It's scaled by the magnetic moment, actually.
I mean, the Z cat. I mean, you're putting these.
This one here?
Yeah.
Yeah. So that one should be easy. There's an easy way of doing it, though I will give away what's coming, but that's okay. Don't see me. Okay. Yeah. It's this one here. It's a localized anion the one that I told you about.
But it's you have two anions in that
Yeah.
calculation.
Yeah. So right. Okay.
So it's just a relative.
It's just a relative. So that, yeah, exactly. This little z here is just the difference z1 minus z2, and then it turns out that, okay, the separation, the thing that I'm calculating is just, it just depends on the relative coordinates, that particular thing, because it's the average separation between the particles, so the center of mass doesn't come in at all. Is that the...
Yeah.
In your
Okay.
calculations, do you actually keep the z stars, or do you project this thing back onto the lowest number?
Oh, it's kept exactly like this, actually. Yeah. But this is just, I should say, it's a parameter, right? It's just like a complex number. This. It's not an operator.
Oh, okay, so
Yeah.
Is that that function down in the left-hand corner? That's the function we're looking at.
Yeah, in fact, this actually, this is just the plot of the probability density as a function of, say, the magnitude of this. So you're right. What I'm really looking at is the sort of average separation between these two. Yeah. So, okay.
So, one more question. So you have these coefficients n, alpha, comma, z in the expression. So how do you fix them? What is the defining property?
This, do you mean in the normalization?
Yep.
Yeah. So for the normalization, the thing, actually that's a really good question. Oh, let me point out, incidentally, I'm totally enamored by this construction, so any questions on this, I'm very happy to answer. Okay, so I just set this equal to 1. And then the other thing you can see is that in this thing, when z goes to minus z, you can see that it picks up e to the I pi alpha coming in. So this is actually, this thing I just take to be real, and then you can see that the anionic factor is coming in because of this, when you take z to minus z, for example. I should mention that this normalization itself has really interesting properties of fractional statistics coming into play itself. I won't go into that in detail, but in these papers they actually outline how that itself can contain information on fractional statistics. I can show you that very simply later, but that normalization is something which is a pretty important quantity in itself. The only thing is you can't extract anything from it. Yeah. Okay. So let me just go back to yeah. So this is this is where it stopped, and now the thing is that you can see this is actually a sort of very quantitative description of what kind of exclusion statistics goes on with these kinds of anions. You can see are they bunching, are they anti-bunching, etc., etc. Okay, so again, coming back to what kind of experiments you might be able to do, there's various suggestions I have. Some may work, some may not work, but anyway, one thing for sure is that we're looking at localized quasi-particles. So you're obviously looking at anions that are somehow localized in the quantum Hall bulk. This paper here is actually a very it's a very beautiful set of experiments have been presented here, where they don't look at fractional statistics, but they look at fractional charge of localized quasi-particles. The way it's done is that obviously in the quantum Hall system you have some kind of disordered potential, and they focus on quasi-particles that are actually trapped in one of those local minima, and looking at the Coulomb blockade coming from these particles, they can actually tell that these particles have, in that particular case, charge E over 3. So they were looking at mu equals 1/3. And by looking at Coulomb blockade peaks, they were actually able to say that these particles have fractional charge E over 3. So the sort of things that I was talking about would be experiments that could potentially be done on these kind of localized quasi-particles. Then there's the question of how do you actually get these particles moving. So I'll come to that. This is another regime where they still haven't reached the quantum Hall limit yet. if that were to happen, there's a whole plethora of things that you could do based on some, and really measurements, and that's a whole thing in itself. I'm happy to talk a little bit about that later. And then finally, the other thing that you could try to do is look at, for example, quasi-particles, from end-state quasi-particles, and ask, can I sort of just do the same thing that I did pictorially, but now using edge states having different sources and different detectors? One question that I still don't know how to answer, and for example, Shin presented some of his results yesterday, is what is the connection between the edge and the bulk? I don't know how to really go in a sort of physical thing. For example, in the numerics that were presented, where the crossover really takes place in a real experiment from bulk properties to edge properties. So if I were to propose anything here, I'd really need to understand how the system is connected at the moment to the bulk properties. So these are all proposals. Let me just leave you with one actual concrete proposal, at least a Gadankan experiment, even if it's not something that's really realizable in the near future in the quantum Hall bulk. So that's going to this whole concept of this beam splitter here. And these sort of experiments that I was telling you about, where you have two sources and two detectors, they've been performed. This was actually a really, really nice piece of work in '87, using just photons, and you can see that, well, the situation is slightly more complicated than that drawing there, but this is what it's like. And essentially, what this is showing you is coincidence measurements of two photons in the same detector. So you say, sorry, not in the same detector, but in two different detectors. So the question that's being asked here is, what is the probability of measuring one photon here if I measure a photon there? And you can see that as they change the position of the beam splitter, in particular, as these two path lengths become the same, you can see that when they're exactly the same, if you have one photon here, the probability of picking up another photon here actually goes to 0. And the reason for that is that both photons went into this detector. So this is really showing you bunching. And the kind of bunching properties that I showed you in that plot there, that's exactly the sort of thing that's being measured in this photonic beam splitter. The same thing goes for electronic beam splitters, and you can show that all these graphs essentially tell you that there's complete anti-bunching going on, which means that if one electron went in here, the other one would have definitely gone in here. So those are the kind of experiments that have been done. Okay, so now we thought, how could you simulate this kind of beam splitter measurement in the quantum Hall system, say in the lowest lambda level? And so the sort of thing that we came up with was, and this was work with Nigel Cooper, was to really introduce a saddle potential. It turns out that saddle potential is a very nice potential because first of all, you can see it sort of, at least it looks kind of like a beam splitter, but in fact it actually turns out to act like one. And what I'll show you in a moment is that if you put a particle here and you put a particle here exactly along these zeros, then the particles tend to propagate towards the center. And then they have a choice. They can either go this way or they can go this way. And what I'm going to show you is that whether they both went, if you have two particles, whether they both went this way or one went this way and one went the other way, actually really depends on their statistics. So this was the potential we chose. It's actually a very nice potential because it respects the anionic boundary conditions. This is really the form in terms of those operators that I had, or rather, yeah, in terms of, it's not going to the right slide, but anyway, it's okay. These operators are the same ones that I showed you right at the beginning. So essentially, you can convince yourself that this kind of saddle potential, if you write it in the center of mass and relative coordinates, first of all, it decouples in these two sectors. And it's also, in the relative sector, it's one of those quadratic operators that I showed you. So it ends up actually being just proportional to one of those quadratic operators. So it really respects the anion boundary condition. Okay, now very quickly, since I'm running out of time, what I'll tell you is if I put a localized quasi-particle here, where would it propagate? How would it propagate? So that's one question that we need to ask ourselves. And actually, to figure that out, we had to go through there's some very nice analogies in quantum optics where X and Y in the quantum Hall, in the lowest Landau level, you know that X and Y don't commute. There's actually a one-to-one correspondence between X and Y in the quantum system and X and P in the quantum optics system. So using these analogies, we were actually able to figure out how a coherent state might propagate in this kind of potential. It turns out that it propagates along one of these equipotentials, and also what happens is that as it propagates along, it starts flattening out. Okay, so I won't go into all the details of this, I don't have time for it, but essentially if you were to place a quasi-particle at some point along one of these, anywhere on the saddle potential, it would go along one of the equipotentials, and as it traveled along, it would also flatten out. So it turns out that's the dynamics of it. The center of mass motion also does the same thing. It's exactly the same as the single particle physics. And for the relative motion also follows one of these equipotentials. It's much harder to analyze than the center of mass motion because of all this complicated algebra that I told you about. But what remains true is that as a function of time, the relative motion is also very similar to the center of mass motion. So finally, if I put two particles like so, I get to my question, do both of them go this way, or does one go this way, and does one go this way? And you can actually guess what the answer might be. It really depends on the bunching properties of these particles. And an analogous question that you can ask is, if you look at y1 and y2, their expectation value, is it positive or negative? That's what you need to be asking. If it's positive, it means they both went in the same direction. If it's negative, the product of these two is negative. That means that they went off in opposite limbs. Okay? So we calculated that, and you can actually, again, I won't go over the details, but essentially what it's saying is if you place them exactly along the y-axis, so these two would be 0, it turns out that more or less the answer completely follows this sort of curve, that same bunching parameter that I showed you. So that means that if the there's a little subtlety there, but more or less this is the answer. So that means that if their initial separation was such that the bunching parameter was positive, then both particles would go that way. If the initial condition was such that it was negative, then you'd see that one went this way and one went the other way. So in that sense, a saddle potential really acts as a beam splitter for quantum Hall anyons. It's not an obvious choice of a potential, but I think it's the best one that one could come up with because it's the simplest potential that respects the anionic boundary conditions.
So in order to see this effect, you have to start them at initial configurations that are within a couple magnetic lengths.
Yeah, that is the issue. That is a bit of a problem, but yes, that is what you have to do. What you'd have to do is you have to have some sort of localized initial potential here where you trap two of these particles, and then if you could have detectors somewhere here and somewhere here, you could ask yourself, did they both go into the same thing or did they go into opposite? Yeah, but the issue is that the initial condition would have to be a few magnetic lengths. So separation. Separation would have to be a few magnetic lengths apart.
But you don't include interaction between them.
Yeah, okay, so, good. So the answer is no for this. I haven't included interactions, and I think that would be really the next step to do.
So use the Atlantic, for example, the prefer to go the same
Yeah,
direction. Then it
that-
would be
that-
difficult to distinguish.
Exactly. So, again, one thing one would need to compare is sort of the length scale over which the interaction plays a role versus this sort of statistical repulsion or attraction, so to speak. So, yeah.
So how big are these particles? I mean,
Yeah, this is the issue though. I mean, I think it's Steve's point also that as you come very close to, within a magnetic length, then the picture is breaking down a little bit. So ideally, you would like to place them as close together, but at the same time have them be well defined. So yeah, so that I think that is the big issue. So, okay, if there are no other questions, that's more or less bringing me to the end of what I wanted to say today. And so let me just conclude. So hopefully I've shown you that these two particle correlations actually carry very useful information on statistics. And then you can see that the anionic statistics actually comes out in this sort of angular dependence that I showed you, that 90 degrees is the special angle, and also an exclusion. Properties, hopefully these, well, not hopefully, these kind of effects are in fact present in quantum Hall systems. It's just a question of what the best way is to explore them. And then I also showed you that, for example, a saddle potential would be a good way of exploring this kind of thing. And finally, I obviously didn't bring any non-abelian states at all, but there's a very interesting question on non-abelian states, namely, you cannot be looking just at two particle correlations, obviously. So one question is, what is the minimum number of particles that, what's the sort of simplest correlator that you can take that shows you braiding statistics or just non-abelian statistics? And that's one question. And then the other related question would be, I showed you this very lovely construction by these folks on the localized anions in the sort of, let's say, something that would correspond to Laughlin states. One more question to ask here is that what is a sort of localized state that you would have to build if you were to describe non-abelian particles? So there's still some, I think there's quite a few open questions with this, and then, of course, in experiment, how much of all this can be seen. So, thank you very much.
Any further questions? So can you back up on one slide? So,
Yeah, I went over that right.
it looks like you're starting the anions exactly in the center of the,
Yeah.
and if you sort of move them just a little bit off, what happens then?
It's a problem. Well, no, it's not. No, it's not a problem in the sense of. Okay, here's the thing. If physically you have a particle slightly above and you have a particle slightly below, so naively you would think that this would just go off here and then this would just go off here. But the point is that when you actually take into account everything, it doesn't just do that, because there's this extra statistical factor coming in. What you do have to worry about is how far above the axis you are. Because if you go too far, then they don't care about each other, they just go in their own ways. But you can be sort of very close enough that, and also you obviously have to know exactly how off you are. But if you know exactly how off you are, you could put that into this part here and then also extract the statistical parameter.
How does it change?
Exactly like this. So this is just saying the same as how far above the y-axis, sorry, how far above the x-axis you are in the center of mass in the relative.
Okay, so it's in that expression, right?
Yeah, yeah, so this is, yeah, how far above you are from the axis of the road. Yeah.
Probably you can find a contribution from interactions just fixing the position of one and the sketching experiment on this one.
Yeah, actually, yeah, that's the thing. Even if you had interactions, the sector, I think effectively what you're saying, the sector that would get affected is really the relative sector. So what's nice about this, in fact, and we've just started looking at this, is again the Coulomb interaction, for example, would come into the relative sector, and that's also something that we've been looking at, but don't have answers yet.
Perhaps a silly question, but if you were going to do this with a monkey saddle,
What's more?
a monkey saddle, okay, you know, a monkey saddle is where there's
Yeah.
also room for the tail.
Aha, okay. That's
So-
wonderful. If it's actually separable and respects, if the monkey respects the anion boundary condition,
that might
I'm
be
ready to
something.
try it. Okay, so what is it? It's like this, and then what?
I guess you would have six,
Oh,
five or six even.
Okay. You mean like this?
Yeah, I'm just wondering how dependent it is on the geometry.
Actually, this is very nice. Do you know what function gives you this?
No, but
Wait,
you can look up some nice function.
It's
I don't know it off by heart, but
Okay,
there is
okay.
something.
Because actually it's very beautiful. It's a very nice question. Okay. It's a nice question for two reasons. The thing is, the first thing to check is if it's separable in these two forms, and it has to be, and if it respects the anionic boundary condition. One reason that it's nice is that you could have all kinds of combinations
Right,
here.
yeah.
And so that's nice, but I should say the reason that I really like that suggestion is that when I started thinking about what you might do for non-abelian states, sort of, I don't know, these are just hand-wavy ideas at the moment, but what I was thinking of was, if you could put 3 or 4 particles somewhere else, can you actually see the braiding, and can you at least, just as a thought experiment, ask yourself questions like, depending on which one went first, or depending on how, could you have different outcomes as to where they actually went off, and then that would be evidence that, somehow there's the non-commuting aspect. So I didn't know that there was this monkey sitting here. Thanks for the information. It would be interesting to try that out, actually. Yeah.
So did you estimate the contribution from second Landau level? Because it's very unstable configuration, so probably any perturbation will change it.
So not for this. I did for some correlators. I didn't do it for this particularly. The one point that I had to say was that this dimension was or this energy U times L squared, that needs to be very small compared to the Landau level of spacing. So that's one thing to keep in mind. I did calculate the contribution here, but I did for the Bunch-in parameter and things. So even there's some appropriate length scales and time scales that actually come in, where beyond which the Landau level mixing gets actually it sort of messes up this result.
Any further questions? If not, I think it's maybe